Okay, this example here is a soil sample collect from field has a mass of 2,000 gram and volumes of 1,190 centimeter cube. And again, like phase diagrams, phase relationship problems. Always start with a phase diagram. Then you have air, water, and solid. And we can start with filling up informations that provided by the questions. Before that, we put down mass and volumes. And for this questions, you stick with the units of gram and centimeter cube. You said it has a mass, which is the total mass of 2,200 grams, and it has a volume, given total volumes of 1190 centimeter cube. And after being completely dry in an oven, so it gives you the hints of the mass of solid, which was 2035 grams, and the values of G sub S is 2.86, and the density of the water, very typical, is also given. So density of water equals 1 gram per centimeter cube. So those are the given informations. And the questions first, like I asked you to complete the phase diagram, find the void ratios, saturation ratio, dry density, total and total density, and part E, find the dry unit rate. Before we go into those parameters that being asked, it's always nice to fill up the phase diagram. Next, we'll look at what we have. Remember, like for mass of air, which always automatically we can say equals 0 for engineering purpose. And very obviously, like if you want to find out the informations, the rest of the unknown here, which is the mass of the water, the volumes, including air, volume of water and volume solid. We find the mass of the water is quite obvious because the mass of the solid plus the mass of water equals to total mass. So we can identify the mass of the water will be equals to total minus the mass of the solid. So with that, we can find out the mass of the water to be 165 grams. After that, this is after that, we know like the density of water, and it serves as a bridge between the mass of the water and the volume of the water. So we can find out the volume of water equals to the mass of volume divided by the unit weight. Actually, it's the density of the water. So we can find out the volume of the water. It's 165 centimeter cube. Then next, we want to find out the volumes of the solid through the specific gravity. And we know the definitions of specific gravity is equals to the density of solid divided by density of water, which is equals to 2.68. So the density of the water, sorry, the density of the solid will be equals to 2.68 grams per centimeter cube. There. And the next, we want to find the volume of solid, which is equals to the mass of solid divided by the density of the solid. So we will find the volume of the solid to be 659 centimeter cube. And after that, we can find out the volume of air, because that will be equals to total volumes minus the volume of water minus the volume of solid. So after that, pretty much we find out all the unknown on the phase diagram. Then we can start answering the questions. First, it asks the void ratios. Part B right there asks the void ratios. It will be equals to the volume of void divided by the volume of solid. Just equals the volume of void, which is equals to the sum of volume of air plus volume of water. In part C, we are asked about the saturations, and saturations is equals to the, as we can see on the FE manual right there, is equals to the volume of water occupied by volume of void. And we know from the volume of void, volume of water is 165, and volume of void is this addition of the two of the volume of air plus the volume of the water. And then we would multiply, we will multiply by 100%. Then we got the saturations to be 38.3%. And then part D, he asked the dry density. So the dry density is given in our FE manual, which is, this is given us the unit rate. But we understand that the rate is equals to, or the pretty much the density is related to the unit rate, because unit rate is equals to the density times the gravity. So for the dry density, will be equals to the mass of the solid divided by the volume. So mass of the solid divided by the volumes. The total volume, in fact. And for the total density, which is really like the total unit weight in the FE manuals, but now we do the mass, not the weight. And the mass, total mass is 2020, 2200 gram, and the total volumes again. And part E, he asks you about the changing the dry density to dry unit weight. And we know again the dry unit weight is equals to the density times the gravity. But that will be equals to the 1.71 gram per centimeter cube, which is density, and then times the gravity, which is 9.81 meter per second square. And we want to convert the units into kilonewtons per meter. And if we play around with units here now, this is we consider 1 kilogram is equals to 1,000 gram. So this set of units here give me the Newton. And then we keep working on our units. We know 1 kilonewtons equals to 1,000 newtons. And also the 1 meter cube is equals to 10 to the 6th time of the centimeter cube. See the units to be worked out. So now the grams is gone, and also the centimeter cube is gone, and now this Newton is gone, and then what is left with is kilonewtons per meter cube. So we can find the dry density to be 16.77 kilonewtons per meter cube. So that's the dry unit weight. Okay, next. There's another phase relationship problem here. Is that the mass of a moist soil samples have a volumes of 0.0057 meter cube, and the weight is given as 10.5 kilogram. Again, it's always good to start with a phase diagram, which have the air, water, and solid. It gives the mass and volume. This time volume is in meter cube and the mass is in kilogram. It gives us volumes right there to be 0.0057 meter cubes and a total mass of 10.5 kilogram. The moisture contents is given, so water content here, and we can check our FE manuals again. Is equals to the weight of water divided by the weight of solid, and this is equals to 13%. And the specific gravity is given as 2.68. And again, like we want to fill in our phase diagram because we always want to complete our phase diagram before we get to answer the parameters. This case, part A, the dry density, part B, the porosity, and part C is the saturations. And for this case, we try to firstly fill up all the informations We also know after putting the total volumes and total mass, we also know the mass of the air is equal to 0. We know like we need to set up equations now in order to solve for the unknown in the phase diagram. So here we use our first equations, and since this is given the water content, which we related to the mass, we better stay with mass here. And it gives you the total mass of 10.5 kilogram. So we can set up another equations. It's the total mass equals to the mass of water plus mass of the solid, which is equals to 10.5 kilograms. Then we will realize we have two equations there, two unknowns. So pretty much we can solve for all the mass. And if we have substitute equation 1 into equations 2, we solve for the two equations there. We got, firstly, we got of the mass of the solid. And we also can easily find the mass of the water. So we know the mass of solid, this is 9.29. And we know the mass of water is 1.21 right here, kilograms. And then next, we always know the density of the water, just equals to 1,000 kilogram per meter cube. And we can take advantage of that. So the volumes of the water will be equals to the mass of water divided by the density of the water. So with that, we can find our mass, the volumes of the water. So that's the nice thing of the phase diagram. Again, we can always use the bridge, like the unit weight of the water, and also the specific gravity, which is equals to 2.6x this case. We know this is equals to the density of the solid divided by density of the water, and the density is equals to the mass of solid divided by volume of solid as reference to the density of the water. If we organize these equations, so we want to solve for this volume of the solid. And actually you realize the equations I'm putting in here is similar to these equations. Just be careful the interchangeable between the unit weights and density. So we put in the informations. We can find out the volume of solid. So first we find out the volume of the solid right here. Okay, and next, if we solve for the volume of void, it equals to the total volumes minus the volume of solid. And also we can find out the volume of air is equals to the volume of void minus the volume of water. And the equations of volume of void actually is also can be found on the FE manuals right there. So we plug in the numbers. That gives us the volume of the air. So pretty much we find out all the parameters on the phase diagram. And with that, we can solve for the parameters that being asked. First, is the dry inner rate, dry density. Sorry, so the dry density will be equals to the mass of the solid divided by the volumes. Again, we can find by these equations here. They ask the unit weights and the difference gravity. So instead of the rate, we use the mass here. And we put in the numbers. And that can be defined as 1,630 kilogram per meter cube. And part B, he asks the porosity. And on our FU menu, porosity given by these equations. You can, if you know the void ratios, you can relate it to the void ratios, or like by definitions, it's just the volume of void divided by the total volume. And total volume of void we found previously right here. So it goes to 0.00223 divided by the total volume, which is given. Lastly, it asks for the saturations. And according to our FE manual, saturations is by definition is volume of water divided by the volume of void. So how much volumes is in the void? How much water is in the void by volumes? And volume of water is 0.0. So again, this is the volume of water here. Volume of water divided by volume of void. And we give us about 54% or 0.54 as our degree of saturation. Okay, a clay samples has a volumes of 450 centimeter cube, a moist weight of 34 kilogram, and a water content of 13.5% in the field. And the samples is collected and then shipped to the lab, and is dry out and then in the lab, and then do a compactions to a minimum volumes to become 9 centimeters by 6.5 centimeters and 3 centimeters. So we get the minimum volumes at dry conditions in the lab. And then it is asked what is the relative compactions for the soil samples. For phase diagram problems and also for soil index properties problems, I highly recommend to start with a phase diagram. It helps you to organize your informations, and you will help you to solve the problem throughout the process. So phase diagram, as we know, with the air, water, and solid. And then put down what is given. It's given the total volumes of 450 centimeter cube. It also gives you the total weight, which is 34 kilogram Additional informations include water content equals to 13.5%. The FE manuals use this Greek letter water content. So let's be consistent on the symbol with the FE menu. So the question asks the relative compactions. It asks for the relative compactions. And we go back to our FE exam menu. It gives you the relative compactions formulas right there. So this is the relative compactions formula. So relative compactions equals to the dry unit weight in the field divided by the dry unit weight maximum, which can be figured out in the lab, and then times 100%. So the key information here now is the dry unit weight. And we go back to our FE exam menu again. The dry unit weight is equals to the weight of solid divided by the volume, the total volume. So the key missing now here from phase diagram, as we can see, is the solid weight. So, but the water content is given. So we can start with the water content to solve these problems. So water contents is equals to the weight of the water divided by the weight of solid. Again, we can find this information on our FE menu. The equations right here, if you can see my cursor. Then we know that the total weight right there. So this is the water content, and this is the total weight is equals to the weight of the water plus the weight of the solid, because we are confident that the weight of air is equal to 0. Now, the key point is to find out the weight of the solid. So if we reorganize this, combine these two equations right there, the water content will equals to the total weight minus the weight of the solid divided by the weight of solid. Pretty much like we substitute equations 2 to equations 1. Then we can ask ourselves whether we are ready to solve these equations, because we know the answer is yes, because we know the water content. Also, we know the total weight, and then we are solving for the weight of the solid. So if we reorganize these equations, we do some simple algebra here. So we try to isolate the unknown. This is capital W. Try to isolate the unknown of weight of the solid. After we organize the equations, we find out that the weight of solid equals to the total weight divided by the one of water content. So we know the total weight is 34 kilogram, and the water content is 13.5%. So with that, we can find out the weight of solid to be 30 kilogram. So we know this is 30 kilogram. After that, we plug back into the equations right here. So the relative contractions equals to the weight of solid in the field divided by volumes, and then divided by the weight of solid. We know the weight of solid is 30 kilogram divided by the volume in the field originally is 450 centimeter cube, and then divided by the weight of solid is 30 kilogram again, but this time is at the minimum density conditions in the lab, and which is given from the questions that it is 9 by 6.5 by 3. And after that, we do our math. We find out the relative compactions to be 39%. Okay, so let's work on some soil classifications example here. We have 3 soil samples here, shown as the grain size distribution curve, and what we want to classify it per the ASTM E2487 standard. First, when I see this grain size distribution curve, first we need to read those axes. So the y-axis is percent passing, and the x-axis is the particle diameter. And it is on a log scales, reading 0.01 here, 0.1, 1 millimeters, and also 10 millimeters. For soil classifications, very important to identify or to aware of the 2 important sift size. The first most important one is the number 200 sift, which is 0.0075, which is right here. So this is the 0.075 millimeters. That is the number 200 sift. So whatever passing number 200 by definitions, those are those the fine grain material, and whatever retained on number 200, that is the coarse grain materials. And coarse grain materials has sand or gravel, and passing it could be silt or clay. And for those retained on number 200, to distinguish whether sand or gravel, it is determined by the number 4 sift. And by definitions, the number 4 sift has a size of 4.75 millimeters. So this is 1, 2, 3, 4. So 4.75 millimeters is right there. So this is the second most important sift, number 4, because it's distinguish the sand from the gravels. So when we first when we approach our grain size distribution soil classifications problems per ASTM standard, the very first thing to do is for each soil samples, we can tell the percent gravel, percent sand, or percent fines. And percent fines is the most obvious one because, again, percent fines is defined by the particles passing number 200. So which we can read straight from the graph. So percent fines, for example, for sample number 1, so we are doing sample number 1 here now, which is the red curve, and as we can read from the graph, for percent passing number 200, we know it's 0.0075 right there, and we read 9%. So percent 5 is the one that pass number 200. And after that, we can look at the gravels. So gravel is retained on number 4. So that gives you the percent gravel. And if we read out this graph now, for examples, we know percent passing number 4 is about 52%, and percent retained is equals to 100% minus percent passing. So we know it is like 100% minus the, again, 52% we're reading here for the number 4 sieve. Then we know we have 48% retained it on number 4. That's the percent gravel. And percent, eventually, then we look at percent sand. Percent sand will be equals to percent sand equals to percent will be the remaining of the particles. So it will be equals to 100% minus percent gravel, also minus percent fines. So if I put here again, so percent sand will be equals to 100% minus percent gravel minus percent fines. So for this case, it will be equals to 100 minus 48% minus 9%. Then for the percent sand, we get is 43%. So after we put down those percent gravel, percent sand, and percent fines, we can start to work it through our ASTM standard. And on the left, you see the pages from the FE manuals. For the Geotech part, the last 2 pages are the soil classifications. One for AASHTO, the other one is for ASTM. So here you see on the left on the screen, you can see the ASTM standards 2487 table here is kind of like a tree-logic diagram. And if we work through it, then we can find the required group symbols and also group name of the soil classifications, which you can see on the right hand side. This is where we want to end at. And from the left, this far left is where we want to start. First, the first columns you walk through it is you need to determine whether this is a coarse-grained or fine-grained material. And as you can see there, now the first thing to determine is whether you have more than 50% retained on number 200 or more than 50% passing number 200. So for this case, we only have 9% passing. So it is more than 50% retained on number 200. So this is our first step. Then we need to determine, so the second column, so now we know this is a coarse-grained materials. We need to identify whether it's gravels or sands. And in this case, we have 48% gravel versus like a 43% sands. So the majority is gravel here. So if we feel the conditions that out of those coarse fractions, the more than half is gravel, even though this case is a little bit close, 48 versus 43 out of the 100. But yet, gravel seems it's the majority of it, so it's a gravel. And then next, next columns we work it through, we need to determine whether it's clean gravels or gravel with fines, and with some sub notes right here. And it highly depends on how much percent fines we have. We are the case that we are at 9% fines, so we are not both less than 5 or more than 12%, but we are in between. We're in between 5 and 12%. So if you read the sub notes right here, sub note C right here. So we are the case that we are between like a 5 to 12% fines. So we need to have the dual symbols. And for the case that we are given the liquid limits and plasticity limit, and the difference between the two give us the plasticity index, which is equals to liquid limits minus the passing limit. For this case, 8. So if we want to determine the nature of the fines here, because we need to determine on the dual symbols whether it's a silt or clay, we look at the plasticity chart. In this case, we have a liquid limit of 17 right here, and we have a PI for 8. It will be right there. So it gives us like a silt. ML stands for silt. So it's a silt materials. So for this case, we will be determined as the silt rather than clay. So we have to, for this scenario, we go for either like a well-graded or poorly graded. But in order to determine where well-graded or poorly graded, we need the C sub U and C sub C, the coefficients of uniformities and also the coefficients of curvature. And that is further determined by the D10, D30, D60 parameters that we are going to put on here. So next things, like we look at the D10. D10 is the particle diameter size at 10% passing. So at 10% passing, go back to our grain size distributions curve again. At 10% passing, we reform our curve right here. So at 10% to determine D10s, what we do is like at 10% passing, and then to see what is the corresponding particle size. In this case, we get about 0.01. And similarly, for D30, we identified the diameter at corresponding diameters at 30% passing. So at 30% passing, we draw a line and then go back to the x-axis. This case, we get about 1.1. Similarly, we also do it for the D60. So D60, 60% passing, the corresponding diameters is about 6 millimeters. So after determining those 3 different diameter size passing, then we can calculate C sub U. C sub U equals to, as we can see on the ASTM manuals, C sub U equals to D equals to D60 divided by D10. We do our math. Would be equals to oops. So this is D60 is 6 divided by 0.1. That will give us 60. And similarly, we do C sub C. According to the equations, is D30 squared divided by D10 times D60. This one gives us about 2. So we get our C sub U as 60 and C sub C equals to 2. And with that, we go through our diagram here as in order to be well-grained materials, the C sub U need to be greater than 4, and also C sub C is in between 1 and 3, which is our case, So we, after all the work, we get our soil classifications as well-graded. But be reminded that the percent fines is since it's between 5 to 12%, so we need to use the dual symbol here. So now we have a silt and well-graded. So the final answer we get is the well-graded gravel with silt. And the symbol here we get is GW-GM. It is a well graded gravel with silt. So that is our answer right there for sample number 1. And for sample number 2, will be very similar procedure. This time, we are looking at the blue curve right there. So again, first step, very similarly, we want to determine the percent gravels, percent sand, and percent fines. And percent fines is always the most like obvious because it's the whatever passing number 200, and we can read it off right from the chart that brings our distribution curve. And here we are reading about 4% right there, passing number 200, because we know number 200 again is 0.075 millimeters. And on this like a blue star here, I'm reading about like a 4%. So it is 4%, passing number 200. And percent gravel again is the material, the soil particles retained on number 4. And this case, this is my number 4. I'm reading about 63% passing because number 4 is 4.75 millimeters again. I'm reading 63% passing. So retained is equals to 100% minus percent passing. So it's equal to 37. And percent sand will be can be easily now calculate as 100% minus percent gravel and also minus percent fines. So we do our math here, which is 100 minus 37 minus 4. So percent sand given in this case is 59% sand. So with those numbers, next we can go to our ASTM like a flow chart again. And first we need to determine where this working through from the left to the right. First thing we need to determine whether it's this coarse grained or fine grained materials. And this case, since we have the majority of soils retained on number 200, as we can see at the very beginning, only 4% passing number 200. So we only have 4% fines, but we have a lot more gravels and sand materials. So this is again, one more time, this is a coarse grained soil. And this case, we have much more sand than gravel because we have like 59% of sand versus like a 37% of gravel. So it is a sand materials right there. And we only have 4% fines right there. So this time it is a clean sand because we have 4%, which is less than 5% of fines. And we need to read the subscript over there. Now this case, we're not like between 5 to 12%. So pretty sure like, we are less than 5%. So we use a clean sand materials. And next thing, like, in order to determine whether it's well graded or poorly graded, again, we need to read it through the D10, D30, and D60 parameters. And this case, we have the D10 values for the samples. We go for 10% passing and then go off our curve and then read what is the corresponding diameters. This case 0.1 again for D10 and D30 again at D30% passing. We read off from the curve. We read about 0.24 here. And at 60%, the same thing, we go off to 60% and then read off the curve. And we have 1 here, 2 here, 3 here. So we had about 3.1 right there. And we also like put down those informations in the formula for C sub U, coefficients of uniformities, equals to D60, 3.1 divided by D10, which is 0.1, so which is 31. Again, C sub C, very similar. We have the same equation, so which is the D30 square divided by D10 which is 0.1 times D60, which is 3.1. And we do our math. This is equals to 0.186. 0.16. So after we have the C sub U and C sub C, we can go to our third column again. In order to for it to be well graded, the C sub U is need to be greater than 6. It is the case, but this is like a conditions of n right there. But this case, our C sub C is not in between 1 and 3, so it is less than 1. So it is the case that C sub C is less than 1. So it is a poorly graded material. So for this case, we can find our group symbols, and for a good name, we also have a further subscript need to like handle here is poorly graded sand, given the conditions that whether we have enough gravel. If we have more than 15% gravel, we need to add like a with gravel to the group name. So this is condition I right there. So we are here, and the case that we have like a 37% gravel, which is greater than 15%. So eventually, our group name is poorly graded sand with gravel. So that is our group name and also our group symbol. So that's the answer for the second soil as S2 right there. And last but not least, for our very last sample examples, S3 soil sample S3 right there, we go through the same procedure again. Very first thing we always need to handle is put down percent gravel, percent sand, and percent fines. And always start with percent fines, because that's the most straightforward one. And we read off from the number 200 SIF, which is right here, 0.0075 millimeters. This times we have 70%. So we read off from this chart, this number here. This is my number. But this is my number 200 SIF, and I got 70% passing. And percent gravel, the number 4 SIF is right up here. So this is my number 4 SIF. Pretty much 100% passing number 4, which means none of it. There's no soil particles retained on number 4. So that is like a 0% right there. And percent sand will be the rest of the materials. So there will be 100% minus 70 minus 0. So I know I have 30% sand. And after I have done that, then let's go to the ASTM table again. In this case, work from left to the right. In this case, we have the majority of fine grain material. So we have 50% or more, which is this case 70%, past the number 200 SIF. So we know it's a fine grain materials. After that, next, since we are not, we assume there's no organic material here, so I assume everything is inorganic. We have the case that we have a liquid limit of 48 and plastic limit of like a 34. So the PI values, the plasticity index, will be the difference between the two. So PI will be equals to liquid limit minus plastic limit. So that would be so again, the PI would be equals to liquid limit minus plastic limit of 48 minus 34. I have PI values of 14 and liquid limits of 48. So if we go to the plasticity chart right here, this is the case that the liquid limit is like a 48 and the PI of 14. So it'll be right here. And we assume there's like a so this is 14 and like 48. And this is the case that we assume there's no organic matter, so it's an ML. So with that, we define our group symbol as ML. And if we further work on our chart for ML soil, it is silt. So we know it is a silt. And we now have a couple of like conditions we need to handle. First, on K, right there, is that if the soil contains like a 15 to 30% plus a number 200, and the case that we have 30%, we are right on 30%, not like less than 30. So let's move on. And the condition L right there. So it's that if the soil contains greater or equal to, and we are exactly 30%, so we are at 30%. And predominantly is sand, and our case is predominantly is sand. So we fulfill the L conditions. M, the next one, M, is very similar to L, but the case that like is predominantly is gravel, which is not gravel, we are sand. So we fulfill the case of L right here. So it's that we need to add sandy to the group. So we know this is like a silt, and we need to add sandy on it. So it's just a sandy silt. So with that, we also classify this soil sample as sandy silt for sample number 3 ML material. First thing to deal with the ASTO method is look at the percent passing from the sieve analysis and go back to the example problems we have on the right hand side. We see 3 soil grain size distribution curve. So start with the very first one is the red curve. We need to identify the percent passing on number 10, sieve number 10, which is 2 millimeters. So we identify 2 millimeters on our grain size distribution curve. So this is 0.1 meters, 0.2 is here, and then this is like a 1 millimeters and 2 millimeters here. So we got a percent passing number 200. Oh, sorry, number 10 at 2 millimeters is about, we read from this curve, it's about 38%. Next is percent passing number sieve number 40. And the size of that is 0.425 millimeters. So this 0.1, 0.2, 0.3, 0.4. So this is number 40, this was number 10, and we are reading about 18% right there. And further on, the AASHTO method also look at still passing number 200, and the size of number 200 is right here. This is 0.075, number 200, and the percent passing, all we need is about 9%. So with these 3 readings here, we check our AASHTO manual for a case that like a number less than number 9. So pretty much it's like all of them except those fine-grained silt clay materials. For the case that we need to fulfill number 14 to be 18, which is the case of under 30%, which is here. And also we checked that our for percent passing is 38%, which is less than 50% right there. So we can call it the group is A1-1. And also we need to check before final confirmations. Let's check the plasticity index. We are getting a liquid limit of 17 and a PL of like a plastic limit to be 11. So the difference of two gives us the PI plasticity index values. So PI equals 17 minus 11. So we get 8. So we got 6. We got 6. So which also, like, fulfill the requirements that to be maximum 6. So we can confirm again, like we put down like the liquid limit equals to 17, plastic limit equals to 11, PI equals liquid limit minus plastic limit. So the plasticity index is equals to 6. And with all this informations, we can call this is A1-A for sample number 1. For sample number 2, we go for similar procedure. Our percent passing number 10 here. So sieve number 10, again, we get this the percent number 10 is 2 millimeters right there. So this is 2 millimeters percent number 10. We go up, we get about 56%. And percent passing number 40. So number 40 again is here. And we get about 42%. Percent passing number 200. We get here, it's just about 4%. So we put all this informations together again for our AASHTO menu. So we have the case that for our number 10 is less than it's greater than 50%. So it does not fulfill A-1 -A. But for the case that like we have less than 50% passing number 40, and also we have only 4%, which is like a way less than 25% right there. And also we check our PI values. This case is non-plastic for all of them. So it's non-plastic. So you fulfill all the criteria of A-1-B. Given that our percent number passing number 40 is 42%, is not greater than 51%. So we don't fulfill like A-3. So we are at, this is the PI, and we are at A-1-B. So that's a sample number 2. How about sample number 3? Here, so for the case of sample number 3, we have obviously we have a fine grain material because we have 70% of fines passing number 200. So if we read our AASHTO menu, we have 70%, which is a lot more than 36%. So pretty much we're here. Since it's just like a fine grain material, clay silt type of material. Now it's time to check our PI values and liquid limit values. So liquid limit for this case is 48. So liquid limit equal 48. And PI is equals to the liquid limit minus the plastic limit. So 48 minus 34. PI value is 14. So for the case that we have liquid limit greater than 41 and PI greater than 11, so we are here, pretty much we're here, because both liquid limits is greater than 41 and for PI value is greater than 11. So we have those two. So we could be either like A-7-5 or A-7-6. And if we further like with our values notes here, sub notes here, we realize that you require the liquid limits to be greater than 30. 30 is the landmark between 7-5 and 7-6. So if the case that like is greater than 30, which is our case now, because our liquid limit is 48. 48 is greater than 30. So per this AASHTO SOR classifications, we belongs to A-7-6. So we can put down here our sample number 3 is A-7-6. We can also further investigate our GI values given the formula here. And if we put in like the percent passing on number 200 liquid limit and passing limits, then we can find our GI values. So for this case, the GI is equals to the F minus 35 0.2 plus 0.005 liquid limit minus 40 plus 0.01 F minus 15 and PI equals 10. And PIs we know that it is equals to 14 F the fine content passing number 200 is 70%. And liquid limit is 48. So if we put down all those informations, our GI values for this soil is 21.6.